So we're going to get started right on time because we got a lot to cover. Thank you everyone for coming to the session. I know it's late in the summit, but this is a good one, I hope. So my name is Jed Sundwall. I run the Open Data program at AWS, and I'm going to talk a little bit about one of our public data sets and how we use Lambda, both to sort of create the data set and then a demo that Ryan, how did you say your last name, Ryan? Obsetis. He told me once, I forgot. Down here in front, he built this demo, but I'm going to talk about it. But if you have questions about it after, he'll be around to do this. So before I start talking about Lambda, which I presume a lot of you are interested in serverless architectures you might be familiar with, I'm going to talk a little bit about Landsat, which not as many people know about. So Landsat is a satellite. It's a satellite program that's been around for about 40 years, run by the US Geological Survey. And it took me an embarrassingly long time to figure out that Landsat stands for land satellite. It covers the entire planet every 16 days and creates imagery of all land on Earth. And so that's an image of Seattle, my hometown, from, I don't know, sometime in the past year. And so Landsat is really valuable data, and it's very big. So Landsat data is what's called raster data. And so it's data that is organized by pixels. So every Landsat scene, like the one I showed you before, is made up of about 840 million pixels of data. And so each pixel represents a measurement of light reflected off the planet. And what's great about Landsat is that it includes visible light, red, blue, and green wavelengths of light, as well as a variety of infrared wavelengths and other kinds of data that we can measure from space. And we add about a little over 500 billion pixels of Landsat data to a public data set every day. It's called Landsat on AWS. So this is just an example of some of the kinds of visualizations you can make with Landsat data. So these are just 3 different combinations of different wavelengths of light. This is Wellington, New Zealand, a nice cloudless day. And so we've got a good natural color image, one that highlights vegetation in red using some infrared data, and then another one that highlights urban areas also using infrared data. So that's a little brief overview of Landsat. I'll be talking a little bit more about it. So what does serverless mean? So first of all, it doesn't mean necessarily, there are no servers. There obviously is a server. It's just a server you don't have to worry about. So it's an approach to software that eliminates the need for you as an application developer to worry about maintaining or administering servers. And your application design is facilitated through interaction with APIs and services, as well as self-created non-server-based APIs. So basically, there are a bunch of APIs that you can create yourself, and then there are also APIs like the Lambda API and other AWS services that you can interact with. And you can build entire applications without ever having to choose what sort of instance size you want, operating system, and maintain patches and things like that to keep the software running. Now, Lambda is really cool. So Lambda is an event-driven computing service that responds to events automatically and runs code based on events. And you only pay for the execution time of the code when you use Lambda. So you can run code really at any scale without ever thinking about servers. And like I said, the code is only run at execution time. Back in the day when I first started hearing about the cloud, this is actually how I imagined the cloud. This is sort of like a place where code would run magically, and now today we actually have that, and it's really cool. So I'm going to tell you a little bit about how we actually use Lambda with the Landsat project, and then talk about Ryan's demo. So first of all, you can sort of see up there, like up there. This is the pipeline of how we get Landsat data and make it available to people. So before I showed you how Landsat is made up of several bands of data, it's like 12 different bands of data. Typically, the way you get that data from USGS right now that produces it is you get a tar archive for each scene. So like that image of Seattle that I showed you, or the image of New Zealand that I showed you, you would get a gigabyte tar archive, just one object from USGS. And then you download it, you unpack it, then you figure out what you need. And when we started looking at building this public data set, we talked to a lot of users, and we found that they would just throw away a ton of data all the time. So they download a gigabyte and be like, well, I only need the visible light, and they just toss everything else out. So it's kind of redundant. So what we do is we kind of eliminate that pain for people by downloading everything. We send it to EC2, we unpack the tarball, and then we make each TIFF, each image of the Landsat scene, and some metadata available as standalone objects in S3. And then what you'll see here, We also configured Amazon Simple Notification Service, SNS, to create notifications anytime a new scene is added and available. And like I said, here's another just sort of visualization of the raster data, like how an image comes together. So what we're going to do with Lambda is take those images, those individual bands of data, and turn them into a natural color image that anybody can see. And we're going to do this automatically, and we're not going to use any servers that we administer for this. So, and as you can see, we're going to seamlessly integrate various services, and what we're going to talk about today are Lambda, obviously I talked about S3 quite a bit, DynamoDB, and SNS. So this is basically what the architecture looks like. And also, if I'm going fast, I want to point out that after I talk about this, and I should have said this at the beginning, Matthew Hansen from Development Seed is going to tell an even cooler story. So I'm going fast because I want to give him plenty of time to talk about how they use Lambda with the Red Cross. So just a little interlude there. So anyhow, so this is basically what the architecture looks like, and I'm going to walk through it now. So this is the SNS notification. So whenever a new scene is added to the Landsat on AWS bucket, it triggers a notification that sends out a message that looks like this. It's just a big JSON blob. And highlighted right there, off like askew, let me go back, actually it's probably a little bit easier to see, is the key name. Give me 1 second here. So the key name that comes with it. So this key name says there is a new scene and this is the scene name, okay? So that's what goes out to SNS. And that is also what's available to Lambda. Now, once we know that a scene is available, we also know that all these different files are available. And this is what I said before. We have all the different wavelengths of light that are available, and this is just a little index file that shows that off. And so when a scene comes in, we can see what's available, and we can programmatically take whatever we want from the bucket and do whatever we want with it. So, and then what we're going to do is we're going to take data, we're going to use Lambda to take data out of the metadata file that comes with a Landsat scene and send it to DynamoDB. And then based on that information, on the metadata, we're going to also deploy some more Lambda functions to do stuff with the scene based on the data that we know about it. So this is what the Lambda code looks like. And basically, we've been able to code based on the structure of the Landsat data. We can programmatically access anything that we want. So as soon as we get the message from SNS, we know where to find everything else that we need. So we can get, just in the name alone of a Landsat scene, one of the nice things about Landsat is that it's named quite well. All the data is named quite well. So we can see in the name, we can see the location of the scene. We can also see the day that it was taken. And then, of course, like I said, we can find all the other files that we want from it. So one of the first things we do, and we actually do this every time a new Landsat scene is added to the bucket, is we take, there's what's called an MTL metadata file that USGS provides, and it's just a text file. And it's full of really great data, but it's a space-delimited file, and it's kind of hard to parse, and it's kind of hard to get through. So we wrote a script, a guy named Jeff Layton, who might be in here, I don't know, he's great. He wrote a script in Lambda to recognize every text file that shows up in the bucket, like every one of these metadata files, and turn it into a JSON object that we can store in the bucket as well. So that's number one. And it makes it a lot easier for us to now see when a scene comes in, is the JSON file there? Look at the JSON file, and we can see in there, is this scene very cloudy? USGS provides some really interesting data along with each scene, like how cloudy is it, and then also what is the angle of the sun? And then based on those 2 bits of information, we can tell if it's gonna look good, basically. So it's like, can we actually see the land, and is the sun at a nice angle that we can see the terrain through like hill shades and stuff like that? So what we do then, so we get the data out of JSON, put it into DynamoDB. We're then able to search, and we're able to say, find us good-looking scenes. Find us scenes that have less than, say like 10 or 20% cloud cover, and that have an appropriate angle of the sun to produce a nice image. Now, this is the genius part that I have to give a shout out to Ryan for. So Landsat scenes are pretty big. The data, it's lossless data, so the files are quite large. Like I said, there are a lot of pixels in there. And so typically, I was always, I'd scratch my head thinking about, wow, I'd love to do stuff with Lambda and Landsat beyond just like the metadata files that we're working with. But the TIFFs are a little bit too big to like actually synthesize and put into a composite image on their own. And so Ryan, being a genius, figured out, well, what we can do is we can actually take each TIFF and convert it into a JPEG first. So compress it into something that, we're going to lose some of the data richness information, but our goal here is merely to produce a nice visual preview of the scene. And so what we do is we use Lambda to take each TIFF, convert it into a JPEG, which is quite a bit smaller, and then we've got 3 JPEGs. So we've got 3 JPEGs of each band of data, and then we can then compile those together using ImageMagick, which is an image processing library that's native to Lambda, it just comes built in, and produce a really nice true color image preview, JPEG preview. And then we can then store that in our own S3 bucket. What Ryan did was, send it to S3, and then we have a nice image, and you can even use that to serve up on a website. Because I don't want to cut into Matthew's time, but there's basically Ryan created an HTML website that you can click through, and it's only sort of Landsat's greatest hits. It's the data's coming in, and we have the site that just sort of randomly identifies good-looking scenes and produces these previews, and you can click through. It's super fast, and it's all done without running any servers. It's awesome. That's what I just said. So thank you very much. So that's a brief overview of Lambda, how we use it with Landsat. And I want to point out, it's a demo. We want to show off really how powerful this tool is. Matthew's going to show off how Development Seed works with the Red Cross, I believe, is that right? To work with OpenStreetMap data using Lambda. Thank you.
All right, thank you, Jed. So Jed's actually said that I was going to talk about something a lot cooler, and I actually think that this is the cooler stuff, and it's primarily what I do most of the time is work with satellite imagery such as Landsat and Sentinel, and not what I'm going to talk about, but I would add, since he talked about all these cool things with Landsat, that we at Development Seed actually do have written a variety of open source utilities for querying. There's an API to get to this data on S3, to query it and download it and process it. So you can check that out at our website, or ping me on Twitter. So, but this project is now. What do I do here? Do I just press a button when I want to advance the slide? The big, no, of course. Okay. So this project is called OSM Stats, and it was originally called OSM Gamification, but we didn't like the term gamification. OSM, who's heard of OpenStreetMap? Okay, less than half. So OpenStreetMap is, anytime I try and explain it, I say, it's like Google Maps, only it's not as good in the United States, but it's generally a lot better when you get outside of the United States. OpenStreetMap is all open map data, and it's a platform for making and tracing satellite imagery in order to generate this open data of roads, rivers, hospitals. It's primarily used in humanitarian efforts after disasters, such as the earthquake in Ecuador. An army of volunteers would get online and try and map as much as they could in the area so that humanitarian teams could get in there and provide relief. So OpenStreetMap is the main platform for mapping out regions of the Earth, and a tasking manager is used to identify critical areas. So you can all go to OpenStreetMap and sign up for an account and get involved and just start mapping like something by your house. It's probably already mapped. Or you could go anywhere in the world. But there's a tasking manager that points people in the right direction to say, hey, we need more data in this area of the world because this is really an area in need. So the top of this is a little bit cut off, but the Missing Maps is an initiative by the Red Cross and Doctors Without Borders to encourage people to map more. And one of the things that they do is, this is an autocorrect thing that happened to me. It says organize marathons. They're not actually trying to get people to go out and run a lot. These are mapathons. So So the Missing Maps is they organize mapathons, and what a mapathon is, it's a army of volunteers, a group of volunteers, and they all get together in one building, or perhaps virtually, and they focus on an area, and they all, for an hour, hour and a half, they focus on trying to map as much as they can for that region. And they had a website of, one of the things that the Missing Maps project provided is a website of statistics of users to keep track of various people's contributions. So we got involved at Development Seed. Oh, here's the people who funded it. Gratuitous plug here. So we got involved with Red Cross to come up with what was originally called OSM gamification, and we said, well, we don't like gamification, we like OSM stats better. So what we did was develop a website of statistics for users and hashtags that they will use when they're actually making mapping updates, so that you can track different groups. So when you make a bunch of changes to the map, you make a commit when you're done, and you could include a bunch of hashtags in there, and that identifies whatever it is that you want to include in there. So the OSM Stats website would offer a reward mechanism for encouraging people to map more. And you can earn badges and stuff like that, just like all those little games that you play on Facebook. And we'd have leaderboards for users and hashtags. So this was the original idea. And I just wanted to show you the website really quick. Can we switch over here? Okay, just to put it in context here before I talk about how exactly we did this. So the goal, again, is to provide real-time, up-to-date statistics of user contributions to different parts of the world on OpenStreetMap. So this is the website for Missing Maps, and we have a leaderboard page. Of course. Doesn't work. Okay, well, real-time demo. They never work. They never work. I had just checked this thing too. This thing has been up for a while. Okay, so we have leaderboards. You can switch back now. It's pointless. I'm not even gonna try to do that again. All right. Well, picture this really cool website. All right, leaderboards. What it gives is the top ranking users with the most commits and the countries that they've committed in, and you can also see the countries that are most actively being contributed to, as well as a list of different hashtags. So this way you could have, in essence, let's say, dueling mapathons, where Team A uses one hashtag for their team, and the other one has a hashtag for their team, and so you can see on the leaderboard this tracking in real time. Okay, so that's the background. In OpenStreetMap, these commits are published every minute, and it's unfortunately a little bit more complicated than that because we don't have all the information available every minute. Every minute, the metadata from the users is published on the OSM website, but it doesn't include any of the geometries. Well, we want it only contains a reference to the geometries, so it has like a node ID or a road ID, but it doesn't actually have the geometry of that road that they either added or perhaps even deleted or modified. And we want that because we want to do things like track, I would have shown you on the website, but we want to do things like track kilometers of roads so that people can earn badges like Road Builder and River Builder and whatever they may be called. So there's statistics that we get from those geometries. So there's another site called Overpass, and what they do is they keep an up-to-date database replication of all of OpenStreetMap, and gets the geometries published minute by minute. So we have two sources that publish new data every minute, and we want to combine those and then make them available also by the minute. So what we came up with is this design, really a microservices architecture focusing on using Lambda primarily, but we do use an EC2. I'm not sure, really, you can't really see this all that well, but there's a cool laser pointer on here, isn't there? All right. So here's the two sources of data, OSM and Overpass. And these are both, so that we have both these APIs. We have an EC2 instance running. And this isn't the focus of it, but it's important to just point out how we get this. We have a EC2 instance with a Docker container running something called Planet Stream. Planet Stream takes in both those data sources. It takes in the metadata, it takes in the geometries, it matches them up in Redis, and then spits them out. And where it spits them out is into a Kinesis stream. Oops. All right, how do I go back? Back. All right. So this is the Kinesis stream. So it puts them in the Kinesis stream, and the rest of this stuff isn't really important. We make the geometries available just so that it on the website it shows the last 100 geometries that have been added to the database. But this is where it happens right here. The stuff is, each change set is entered into the Kinesis stream, and we have a Lambda function that, as these events are added into the stream, the Lambda function all right, I already talked about that. Okay, so we have an AWS Lambda function in Node. It's mapped to the Kinesis stream, and when new events are added, the Lambda function gets them automatically and calculates a variety of metrics from the geometries and from the metadata, including like where was this edited, what countries were this edited, and then that gets added to a database that's running on RDS. For deployment, we deploy this by using Python script in Bodo 3. We first deploy the database. It's important to sort of get all these things in the right order. First deploy the database and migrate that and create a rule so that we can access, this is important for later, create a rule so that we can access it from anywhere. Then we create the Kinesis stream, it's just an empty stream at that point, and a Lambda function, map it to the Kinesis stream, but nothing's going on, of course, at this time. Then, finally, what we do is we deploy the EC2 with Planet Stream, and now data starts going into our Kinesis stream, and the Lambda function automatically is now putting that into the database. So why Lambda and Kinesis? So there's some real advantages to the microservices architecture here. Of course, these are general pros for microservices is that you can replace these components. This was particularly important to us because we wanted to be able to replace Planet Stream somewhere down the line with something that was a little bit more scalable and easier, because right now we're relying on this other API to provide the geometries that's not entirely stable. And we also wanted to do some historical processing. So Planet Stream is focused on getting up-to-date minute-by-minute changes, but we wanted to go back in time a few years at some point and be able to update the database with data over the last few years. And so this was appealing to us because we could replace the parts as needed, and the Lambda function and the Kinesis stream could stay exactly the same as they were. Whatever we wanted to add into the stream would automatically get processed by Lambda and added to our database. So we could simultaneously be running Planet Stream to get these real minute by minute, as well as another script maybe that's going back and processing historical data and entering that into the stream at the same time. But the most important reason really for going to Lambda is that, I think I have a plot here, which doesn't come out very well. But maybe you can see the general trend here, which is this is a plot of the invocations of Lambda over time. So, but you, of course, you can't see any numbers. But it varies from a few thousand per hour to maybe 0. Because, as I said before, we have these mapathons. So the normal level of commits to OpenStreetMap for the project is, I don't know, maybe somebody's adding something at one point. So you might have a few commits here and there. But then you get all these people in a room together, and now they're making thousands of change sets per hour. And we didn't want to have an EC2 up that was ready to process, and we didn't want to have to worry about, other. Lambda was the perfect solution because it's low cost, and when it's not processing, it doesn't cost us anything. So that was key. And then this is showing the duration down here of the Lambda function, which is generally less than a second. Some lessons learned. We didn't use a local testing framework for the Lambda function, but there are some out there. I think that I would advise anybody to look into doing that if you want to use, especially the more complex your project is. I think this is a pretty important thing to do, is to have some sort of local testing framework so that you're not having to push to Lambda and test things out. And the Lambda logs, Lambda the logs automatically get pushed to CloudWatch, which works great, but it does take some familiarity with figuring out how to access those logs. We use the AWS CLI, which works pretty well, but AWS Logs is a open source project that we ended up using, and it works great for being able to just say, give me all the logs within the last hour from this Lambda function, and show it in my terminal with some pretty colors so I can see the different fields. So I would suggest using that. But the most important thing I think that we learned when using Lambda functions is the fact that error handling is exceedingly important, very important. You do not want to push a Lambda function of code that mostly works. That's something that you can get away with in other systems, but with Lambda, and especially with regard to using it with a kinesis stream, because if your Lambda function errors out, it'll restart on the same event, and it'll do that over and over and over again until your data expires 24 hours later, or 7 days later if you pay for the 7-day retention of your data. So what you want is you want to be able to handle your errors in an intelligent manner. If it's a transient error, such as maybe a website's down or something like that, then yeah, in that case you want your Lambda function to start up and retry it again, and that's fine. But if it's any sort of code-based error, you want to catch that and not return a failure. You want to return a success and log it. So extra work on error handling. You really want to focus on that. Another issue that we ran into was database connections using connects in Node with Lambda, and I'm not sure of the actual details, the specifics of the Lambda container reuse, but Lambda functions there's a container that's running a Lambda function, and that container is reused over time. What we ran into was a case where we kept on getting these database connection errors because we had our minimum pool size set to 1. And so it tried to force keeping this database connection open in the same container until the container expired. And so it kept on failing. So once we dropped that down to 0, which basically says, okay, we don't need to keep this connection alive anymore. Lambda Security and VPCs. Another issue that we had run into, so initially we had this great idea that we would configure RDS to be closed within a VPC, And the way that you do that with Lambda, and this is actually a very new feature in the last several months, that allows you to add a Lambda function to a VPC. So we're like, okay, great. Add the Lambda function to a VPC, give it a security group, give a security group to your RDS, and pair those together. So you give them permissions to see each other. Your Lambda function should now be able to see your database, which worked. It worked great. It was fine. Unfortunately, as soon as you add your Lambda function to a VPC, it can't see any of the rest of the world. It can only see what's in your VPC. There are solutions to that, which we didn't end up trying to figure out. We instead just opened a hole on our database to the outside world. And took our Lambda out of the VPC. So if anybody has an elegant solution for how to do that, I have an idea for how that might be done, but if you know how that might be done, please let me know. I think that's pretty much it. All of our work is open source, and it's available on the GitHub Red Cross GitHub page. And you can also see various blog posts about this on our website at developmentseed.org. Yeah. Oh, we also use Lambda. One more thing. We do use Lambda. I mentioned before about the satellite API for Landsat. Another application of Lambda functions is we use Lambda with API Gateway, and that's how that API works. So the API Gateway provides endpoints, and that actually calls a Lambda function, which provides the actual data for querying what is available for Landsat and Sentinel data through there. Yeah, any questions?
Great talks, really nice work. I just wanted to ask, in terms of the Lambda scalability, could you just talk a little bit more about maybe some pain points that you ran into or solutions in terms of scaling, let's say for hundreds of thousands of concurrent executions of your Lambda functions, and if you hit any pain points with that and how you worked around that?
I can answer that because we didn't actually encounter any problems with that at all. That was what worked the best. I mean, the beauty of Lambda was that we could put whatever we wanted into the stream, and Lambda would automatically fire up 100 Lambda containers and just start going at it. Now, if you had a much higher, so we were dealing with maybe a few thousand change sets per hour. We never had to deal with really, really big scale stuff. If you're familiar with Kinesis at all, we only use one shard. And one shard was enough for our throughput to write to that stream, and it was enough to, for Lambda to, you can read it a lot faster than you can write to it. So yeah, that required no work on our part.
Sort of to piggyback on the last question, and this is either for you or for the first presenter, how do you deal with database connections at a large scale, making sure that you keep the pool of connections low, and then also handling outside providers. Like say I want to connect to Redis through Redis Labs instead of Elasticache, but I also want to have my Lambda functions inside of a VPC. And is the only way to do that by creating a NAT gateway instance?
Yeah, so I think you're onto it right there. So that's the way. If you want to put your Lambda function in a VPC, then you need to set up a NAT gateway somehow in order to have that Lambda function also access outside areas. With regard to the database connections, I really, maybe not the best person to ask about this. I rely on Next to manage database connections, and we set the parameters to have no more than 25 connections. This all seems to work well, but again, we didn't deal with really, like there's a lot of fluctuation in the amount of data, but we didn't deal with like the tens of thousands, like way on the upper end, where some of these things might require a bit of a different design on that, and either more shards and probably something with certainly a bigger RDS instance and more connections available to it, I guess.
Hi, I have one question. Did you choose the Lambda just because you don't have to manage servers, or you do the cost benefit analysis that Lambda services will be cheaper than setting up a server and running it?
Yeah, so our Lambda, our price to run Lambda, don't tell AWS this, it's zero. It's effectively zero. Like, that's how cheap Lambda is. It allows us to offload. That doesn't mean that you guys should raise the price on it either. But we're dealing with such a few number of invocations, even if it's thousands per month, it comes out to cents. So yeah, it allows us to offload the EC2 and still be able to get that scaling when we need it without having to pay for it. Near zero as well. Yeah. Yeah. Any other questions? Processing intensive jobs for Lambda. I mean, this is really what the Landsat thing was if you want to talk to that, Ryan, but there's
So the processing the Landsat imagery kind of involved having to appropriately manage asynchronicity with the functions that I would write for the demo. And what we would do is make sure that we were what we were trying to do was within scope of what the Lambda function was capable of doing. Because as you may or may not know, most any executable that you can build on Linux, you can actually deploy into a Lambda function. For example, like if you wanted to use a CLI instead of one of the SDKs within a Lambda function, you can do that. There was also a open source image processing library that I originally tried to do for the test case that we had called GDAL, GDAL. And what I was trying to do with that was process the scenes, the TIFF files, and then be able to maintain their original resolution and not have to downscale them. Because the original kind of idea for the demo was that we would do true color images that were pan sharpened and just maintain the original resolution and all of the image fidelity. But the third part, the open source library, the GDAL library that we tried to use would quickly max out the Lambda function. So it's kind of a process of trying to make sure that what you're trying to achieve with a Lambda function or multiple Lambda functions in tandem is within the scope of what is ideal to do with a Lambda function, and then where the boundary is between what you can do with a Lambda function versus what you'd actually have to run on an EC2 instance. Any other questions? I'll be around, and Matt will be as well for questions after if anyone has anything.
Any idea when Python 3 will be done?
I cannot answer that question yet. I'm just going to punt to reInvent, and then they'll tell you then.
Or maybe they won't.
Or maybe they will not. I don't know. But yes, we'll be around for questions afterwards.